In this short video, we will look at the conservation of energy for a control volume, but we'll start with the conservation of energy form for a control mass. In words, basically the left-hand side tells me the rate of change of energy inside my control mass. The control mass energy increases if I got heat or work going into the control mass, and the control mass energy decreases if I got heat or work leaving the control mass. And just some technical details over here. Rho is the density, multiplied by dV gives me the mass, and then little e is the energy per unit mass. So if I multiply that by the energy per unit mass, that gives me the energy. So this entire integral becomes the energy. And the energy per unit mass has three pieces to it. It's got the internal energy piece, it's got the kinetic energy piece per unit mass, and it's got the potential energy piece per unit mass, right? And so the right-hand side, in more general situations, where we have forces acting inside my control volume, body forces or forces acting on the surface, might be due to shear forces or other kinds of forces on the surface. The general form of the equation looks like this, and we saw this earlier as well. And so the right hand side is going to be simply the net outflow of energy going out of the control volume as a result of heat transfer. And remember, this double prime means heat transfer per unit area, energy per unit area per unit time, leaving the control mass. And these two terms over here are the net work that's being extracted, because it's got this negative sign next to it, that's being extracted from the fluid because of surface forces. Again, the double prime is surface force per unit area acting on the control volume, and the work that is associated with that. And this term represents the work associated with the body force per unit volume. Remember, the triple prime indicates per unit volume, and the work associated with that. And so all of these things lead to a reduction of the energy of the control mass, right? So if this term is actually positive, then the negative sign plays a role, and the energy will be decreasing. If this term itself is negative, then the negative times the negative makes this a positive term, in which case the energy will be increasing, right? So that's the way to view this equation. And in order to extend this from a control mass to a control volume, we use the Reynolds transport theorem. That's the theorem that provides the bridge that we need. So the rate of change of energy inside my control volume plus the energy going out minus n inside my control surface equals sum of all the forces, work done due to forces, as well as energy transfer due to heat transfer on the right hand side. This is the form of the what I've done is the left hand side is where I've used the Reynolds transport theorem. All right, now it turns out there's a piece of this work that is pertaining to pressure. Looks like this. It's the integral of P, the pressure at the surface times the relative velocity times the area. So since that has the same form as the relative velocity times the area, I can move it to that side of the equation. And so the form of the energy equation can be simplified and written in this manner. And then over here, the only kind of surface force we have are the tangential forces, and the normal force due to pressure has been taken out and accommodated on the left-hand side. All right, so this is sort of the most general form of the energy equation, starting from a control mass, but now converting it to a control volume through the Reynolds transport theorem. On the next slide, I'm going to show you some of the more practical forms of this equation that is actually useful for us to solve real problems, right? So, so there's a steady flow energy equation. So when the flow is steady, clearly this unsteady term is going to drop out. And clearly some of these integrals are just going to become simple products when you have uniform flow assumption or one-dimensional assumption. So here's an example. We have the steady form of the energy equation. So m dot might be the mass flow rate, and this is the total energy out. H over here is the enthalpy. H is simply the U tilde plus P divided by rho, right? That's the definition of the enthalpy. And so this is the energy at the outflow. This is the energy at the inflow inside a one-dimensional control volume, and that has to equal the rate at which energy might come in due to heat transfer, rate at which energy leaves the control volume due to heat transfer, and this may be due to work that's being done, due to an external shaft work that might be delivered to a control volume, or this might be the work that might be extracted from my fluid going through my control volume, and since it's extracted, that would have a negative sign. And then in general, you could have viscous losses, and the viscous losses will always lead to a loss term, and so this is going to be minus W dot viscous losses, right? So this is the form of the energy equation that might be more useful for applying to a real problem. Same form, the only distinction here is I've divided both sides of the equation by m dot. So if I divide both sides of the equation by m dot, this is the result you're going to get. And also I've rewritten this in a manner that I got the in term over here, the out term on the right. And so what I have left with is the net Qn and the net W shaft in terms with the negative sign in front of it, just so we are comfortable using different forms of the equation. And then simply because I got the in term over here, this becomes a plus W viscous loss. So this one is not, this one has everything has the units of energy per unit time. This one, everything has units of energy per unit mass, right? So, and the way you move from one to the other is taking into account this m dot term. So this is the steady flow energy equation, and this is the form that appears in Frank M. White's textbook, 8th edition. Now, we also talked about stagnation pressure previously. I'm going to talk about stagnation enthalpy. And so the stagnation enthalpy in differs from the stagnation enthalpy out only if there's heat transfer, shaft work, or viscous work between inlet and outlet. So if you think about this expression right here, this is what we are stating in words, right? So if I ignore any changes in elevation, so if I ignore this term h plus v squared over 2 is simply the definition, if you will, of the stagnation enthalpy. So it's the enthalpy plus the kinetic energy per unit mass portion, and we can define this to be the stagnation enthalpy H naught. So this is the stagnation enthalpy at the inflow, this is the stagnation enthalpy at the outflow. So in words, the stagnation enthalpy in differs from the stagnation enthalpy out only if there is heat transfer, shaft work, or viscous work. So one of these terms have to be non-zero, otherwise these two terms would be precisely equal to each other. Steady flow energy equation using head form of it is also useful, and the head form of the equation is shown over here, and essentially it is this form of the equation divided by G, and then I've broken up the enthalpy as P over rho plus U, and then both of those terms are divided by G. So that's the head form of the same equation as above. And so all of these terms are going to be head associated with energy transfer due to heat transfer, head associated with work transfer due to shaft work. This is a head associated with any viscous loss terms that might occur in my system. Okay, so this form of the equation might be useful if you prefer to work in head form of the equation. So this is the steady flow energy equation, and I want to reference that to equation 370 in the book. So these three forms of the equation that are summarized in this slide are probably very useful and practical for a number of problem situations.